Okay. Um, so we're going to continue where we left off last week, which is still in chapter two, and I believe that yeah, we have like just a few more problems. In fact, chapter two has nine problems, and last time we ended at 8A, and we now have technically two problems, and of course, for each problem there are a couple parts, and of course, we also need to go back to problem 3C, which we kind of answered last time, but then we didn't show any work or did any proof here. So what we're going to do is we're going to once again uh, try to uh, see why our claim actually works. So go back to problem three. Um, well, let's go back to the big picture of problem three. It says, oh, I'm going to close this here so we can actually see it better. So problem three asks, for each of the following questions, begin by compiling some data. Next, examine the data and formulate a conjecture. And finally, try to prove that your conjecture is correct. But don't worry if you can't resolve every part of this problem. Some parts are quite difficult. Now, again, we actually have already solved part A and part B, where part A asks, what possible odd numbers A can appear in the primitive Pythagorean triples ABC. And our answers is basically all the odd numbers except A equals 1. And of course, for primitive Pythagorean triples, we're thinking of right triangles and of course relate to the Pythagorean theorem, a squared plus b squared equals c squared. And by our assumption, we're trying to think it like middle school algebra, that the right triangle that we're thinking of is just are just lying on the Euclidean geometry, or just grade school geometry, that we're assuming all the values of A, B, and C are first of all positive, and second of all, the sum of the angles of the triangles will be exactly equal to 180 degrees. Now, again, what is a Pythagorean triple? A Pythagorean triple is a set of three numbers A, B, and C, where A, B, and C are integers such that uh, A squared plus B squared equals C squared, which satisfies the Pythagorean theorem. And if we want it to be primitive, then the GCD, the greatest common divisor of the three integers A, B, and C, has to be equal to 1. So now, enough of recall of the definitions. We actually need to come down to problem C here, which is asking the possible C that can appear in the primitive Pythagorean triples ABC. Now, in last life, we saw that would be can appear. We actually came up our solution, but we didn't verify it. So this time we're going to start from here and going to verify why this answer is correct. So, in fact, we actually can go back to the solutions from some of our answers, such as going back to problem one here or problem two. We actually can see some of the reasons why those must be true. Okay. Now, we can actually see that if we try to pick some examples here, for C, we have a 3, 4, and 5, where of course C is equal to 5 in this case. We can also have something like uh, 5, 12, 13, where 13 is of course the value of C, and then we have something like 15, 8, 17. We saw that example, something like that. So now the question is, how can we actually prove that it has to be true? Well, here's the deal. First, we're going C has to take the form of If we're trying to divide the value of c by 4, it has to be the remainder 1. Well, this is because we actually see that 1a is the second part of it. We can simply list out that why our the value has to be a multiple of, has to be congruent to 1 mod 4. Okay, so we can assume in the following way. So notice that uh, as uh, as a primitive Pythagorean Pythagorean triple, a is actually equal to, again, a is an odd number, so we can assume that a is equal to some 2, let's say 2n plus 1. And b is an even number. In this case, we can say is 2n. And of course, for some m and n positive integers, so, or natural numbers in this case, okay, like this. Thus, by Pythagorean theorem, we have c squared is actually equal to a squared plus b squared. So far, this is our basic setup. And of course, now we're going to use our definitions of a and b to show that it has to be congruent to 1 mod 4. So how do we do that? Well, now we're going to do a substitution where a is given by 2n plus 1, where b again will be replaced by 2n. So in fact, what do we get? We get the following. If we try to satisfy uh, our condition here, where a is equal to is an odd number and b is an even number, now as we expand on these two terms, we end up with a squared equals 4m squared plus 4m plus 1. And for b squared, it will turn out to be 4n squared. Okay. Now, of course, we see that c squared has to be congruent to 4n plus 1. Uh, or 4k plus 1. Well, we can kind of group them all together. We have, again, factor out all the 4s, so we end up with 4 times the quantity, m squared plus n squared plus n. And then after that, we set up the plus 1 here. Okay, great. So we end up with the form like this, but this only shows that c squared is taking the form 4k plus 1. That doesn't help us to show that c itself is also congruent to 1 and mod 4. So how are we going to connect this to our idea? Well, we can now try to think of how to come up with the idea of this part, the parentheses, has to be uh, has to be a multiple of 16, uh, or it could be a multiple of 9. So the goal here is not just to end up with c squared is congruent to 1 mod 4, of course, we want to show that um, c itself is also going to be the same. Now, of course, it would be very easy if we assume that c is congruent to 1 mod 4. Well, that of course will imply this expression here, the expression that 4 times the quantity plus 1. But now we need to do it the other way, because we also know that uh, suppose that c is actually congruent to 3 plus 1, we might actually end up with the fact the form that is going to be c squared is going to be equal to 4 times some number plus 1 as well. Okay, so the question is how we can actually end up with this part. Well, so I need to remove this, by the way. Okay. Now, on the other hand, we also need to show that the heck cannot be a multiple of 3. But this part actually it actually comes from the answer of part 1a. Now, go back to part 1a of this chapter. We actually have shown that uh, either a or b must be a multiple of b of 3. And at the same time, we also need to show that c cannot be a multiple of 3 because of this reason. That is again because based on the charts here, if we assume that c is going to be congruent to 0 or multiple of 3, then we actually need both a and b to be a multiple of 3 at the same time, meaning that a, b, and c are all multiples of 3. Then these three values will not be relatively prime. Or in other words, the GCD of all three values would not be equal to 1, but it will be 3. And that's why it actually will contradict with the definition of primitive Pythagorean triple. Therefore, on the other hand, we can also answer here from problem 1a. We have C cannot be, or in fact, it cannot be congruent to 0, or we can say that c squared has to be congruent to 1, by the way. But then it actually gives out either 1 or 2. But again, ultimately, we just end up with not going to be congruent or equivalent to 0 and mod 3. So I'm going to put it. And then now if we combine the two conditions that we found, we can say that therefore C has the form of 4k plus 1 not a multiple of 3 or we can just answer it the way all C's of the form 4k plus 1 that is not a multiple of 3 can appear in a primitive Pythagorean Pythagorean triple A, B, and C. So that's how we can conclude our proof. Now again, how will it look like? Well, it's going to look like the following. So it actually takes on two parts. Okay, first part is to show that C has to take the form 4k plus 1. And of course, in order to do that, we need to show that C has to end up with the form 4k plus 1, not just a c square. Okay, so right now actually see that c square has to be of the form 4k plus 1, but then this is not enough because we actually need to show that uh, C itself has to be of the form 4k plus 1 as well. Now, on the other hand, we just have the conclusion that C cannot be a multiple of 3 here, because if C is a multiple of 3, then we are forcing both A and B to be a multiple of 3. Okay, let me change this here. Okay. Here comes the typo. And then if we combine the two conditions, we will actually end up with our conclusion. Now, again, how should we show that this C square has to be C has to be equal to 4k plus 1? Uh, well, we can try to come up with with the condition here. Okay, so here we actually will end up with some scratch work. Here's the scratch work down below. Now, if we are trying to show that C is of the form 4k plus 1, then we know that C square would then be the square of 4k plus 1, of course, plus 1, which if we try to multiply out, we end up with 16k square plus 8k plus 1. And this implies that and I'm going to use again modular arithmetic here. Why? Because now we're not just trying to divide the results by 4 anymore and find the remainder. We actually will try to divide this by 8. And if we try to divide this whole thing by 8, we will actually end up with one single value, which is 1. Okay. In other words, we actually see that we actually can see that this value here is going to be congruent to 1 mod 8. Okay. Now, of course, if you try to go back the other way around, we also can conclude that here if C square is congruent to 1 mod 8, it doesn't really help us because we can try anything like 3 square equals 8, 5 square equals 8. That means that no matter what square we're trying to use, as long as we have an odd value, if we square that value, it's going to end up with 1 mod 8. Okay. Now, is it going to help us? Actually, it's very hard to tell, but we're going to figure out if it works. Let me try to put a P here. So once again, our goal is to try to end up with the form 4k, well, not 4k plus 1. In fact, we need to actually have a form of 16k squared plus 8k plus 1. Or something very similar to it. And again, here we're trying to analyze this part, the 16k squared plus 8k. Now, if we try to factor out 8k here, if we try to take another root and another root and see what's going on, we actually will get after factor out 8k, we end up with 2k plus 1 here. Okay. Now, why does it matter? That's because if we try and factor out this way, then we can try to analyze what this part can kind of maximize for us. So what do we get here is is that, well, we can clearly have this part not to be of the form that we want. Uh, but now we need to trace back what b is, because we see that we try a couple weights and it still doesn't work, and none of the weights actually can directly give us the answer. So let's see. Oh, here is a mistake. So what do we have here? We have, if we go back to problem B here, we actually show that B has to take the form of 4n instead of just 2n. In fact, it means that if we try to go back to up here, if we change our B to 4n, then the entire game will actually change, because if we do so, we actually will end up with something like this. So this time I'm going to factor out in the following way, and it will actually end up with the answer that we need to show that um, c squared is actually congruent to 1 mod 16, which implies that c itself has to be congruent to 1 mod 4. Okay, so what does that do to the game? Here is the deal. If we try to rewrite the b the form of b from 2n to 4n, what we have is, of course, instead of having 4n squared, we have 16n squared. But that is going to help us the entire game into the following way. So I'll just factor out the 4n between the first two terms, which ends up with, after factoring out, we'll have m plus 1. Okay, and then I'm going to put the 16n squared in the middle, and then leave the constant 1 at the end as the last term. Okay, so far this is what we get. Now we're going to analyze what this part is going to give us. This part is going to give us let's see, 2n. Okay, this is good. This is good. This is good. Okay. So we factor out the m here, and then we have the m plus 1 here. That is going to give us at least one of the parts is going to uh, 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 going to give us something. This is going to give us an even number, because we have either m is even or m plus 1 is even, meaning that the product of m times m plus 1 is going to be even, and then times 4, meaning that this entire thing for n times m plus 1 is going to be a multiple of is a multiple of 8. Then we of course have 16n squared plus 1 here. Now what we need is, well, we also need to have a relationship between a and b, so that we can show that c squared has to be written as a form of the perfect square. Okay, and again, that is because um, uh, c is an integer, and if we square it, it will be a perfect square. So we need the entire thing to be a perfect square. Okay, so in this case, what do we need? Well, if we try to go back to, again, problem A and problem B, we actually can get some help here. We see that uh, in order to get the results that we need, we have to have something like uh, the similar argument. We need to set our n uh, to uh, to be half of m times m plus 1. Okay, and again, that is going to give us that this part here, m times n plus 1, is going to give us 2n, so that we'll be able to get a complete square. So now we're actually all set. How do we end up with our answers? We're going to do it following way. By setting c equals, we're going to write n, we're going to write everything in terms of n, for the sake of our calculation here. So we are going to end up with 4n plus 1 here, but then again, n itself is going to be of the form what is it? 4n plus 1, where n itself is going to be m times n plus 1 all over 2. So the entire thing is going to turn out to be 2n n plus 1, which looks very similar to what we need. Okay. And then we're going to set we're going to set our, again, we need our n, a to be 2n plus 1, and b is going to be equal to 4n, where n itself again is going to be 2, well, it's going to be n times n plus 1, or divided by 2, for some m going to be equal to, well, not equal to, some integers, positive integers. Okay. And again, when we say positive integers, we do not include uh, m equals 0. Okay. Then now, this is that going to be enough? In fact, it is going to be enough, because if we try to figure out what c is, that clearly is going to satisfy the first part, where c is congruent to 1 mod 4, and then at the same time, it actually can show that c cannot be a multiple of 3. Okay. Clearly, if m is a multiple of 3, or congruent to 0 mod 3, then c is going to be congruent to 1. Where c, if m is congruent to 2 mod 3, of course, we still have c is going to be congruent to 1, because 2 plus 1 is going to be equal to 3, which is going to be congruent to 0. So the whole product is going to be 0 plus 1, and then we have plus 1 to end up with c is going to be congruent to 1. Now, last but not least, we can check what happens if m is going to be congruent to 1. Okay, if m is going to be congruent to 1, from now on I'm going to say equal instead of congruent. If m is equal to 1, then we have 2m, which is equal to 2 times 1, which is equal to 2, times the quantity m plus 1, which is 1 plus 1, which is 2. Again, we have 2 times 2 is equal to 4, which is equal to 1. And then plus 1, we end up with c is going to be congruent to 2, or yeah, equals to 2, instead of a multiple of 3. So this, in fact, here, expression, the expression c is congruent, is equal to 2m times m plus 1 here, is in fact satisfying the condition that c has a form of 4k plus 1, that's a multiple of 3. Okay, so again, that is going to include almost all the cases, such as when m is going to be equal to 1, then we have c is going to be equal to 5. Okay, and then if m is equal to 2, then we have c is going to be equal to 13. when c is equal to 3, we have well, I mean, when m is equal to 3, we have c is going to be equal to what is it? We have 3 times 2 is going to be 6 times 4. We have 25. Now we're of course we're trying missing something like 17 and 17 like that. Okay, and we're gonna go over that later to see how we can avoid that. Okay, so but the idea is how we actually try to find out the c value here. Okay, so we can actually see that in this case we have the setup that such that c is going to be congruent to 1 mod 4 and not a multiple of 3. And then after that, if we try to plug it in and do our calculations, we will be able to end up with the fact that c squared is going to be well, a squared plus b squared is equal to c squared, as we expect. Okay, now to be more precise, if we want to prove that our condition c has to take these two has to take this form here, we can actually try to combine the two conditions together. And again, we're going to combine these two conditions together by using modular arithmetic, which actually makes it a lot faster. So here is the true solution that we can actually do, or the actual proof, the actual proof that does not leave any scratch work, but actually we'll get a complete result. So all the c's of the form 4k plus 1 that is on multiple of 3, if we try to combine it with modular arithmetic, which it actually means that c is actually be equal to 12k plus 1, or c is equal to 12k plus, not 12, 12k plus 5, can appear in the primitive Pythagorean triple. And again, now of course I'm going to clarify that except c equals 1, of course. We need to take that out. Clearly, when c is equal to 1, there's no way we can actually make a primitive Pythagorean triple, because the 1 squared is just 1. We end up with a squared plus b squared equals 1, and this in fact is the unit circle. And the only way that both a and b are gonna be integers would be when one of them is exactly equal to 0, which contradicts the condition of Pythagorean triple, because we need all integers are positive, not 0. Okay. Now, of course, we need to exclude that. So, how come we end up with c is in the form of 12k plus 1 or 12k plus 5? Well, let's think about it this way. In order to have 4k plus 1, what we need is, if c is going to be divided by 4, we end up with the remainder to be equal to 1. So if we have the form 12k plus 1, of course, divided by 4, we end up with 12k is going to be divided by 4 is just 3k, and then we have 1 remaining. Now, for 12k plus 5, we have 12k plus 5 equals to 12k plus 4 plus 1. And then we can factor out the 4 from the 12k and the 4 parts, so that we see that the sum 12k plus 4 itself is a multiple of 4, and then we have a remainder 1 here. Now, is there any more of the form 4k plus 1? Yes. We can end up with 12k plus 9. And again, we can use modular arithmetic and also the Chinese remainder theorem, which will appear later on this textbook, to show that these three are the only possible solutions for that will take the form 4k plus 1 as a um and one of them, or precisely 12k plus 9, is the only one that is also a multiple of 3 simultaneously. And of course, we don't want a multiple of 3. So we eliminate that. We end up with these two possible outcomes. So here comes the actual proof. So by setting C equals 12k plus 1, or we can change it to 13 if we want, but it doesn't really matter here. Some k is a positive integer that is not 1. So our proof will be very similar to how we did in part A and part B, by the way. So again, here, if we set up this way, then we need to figure out what A and B are. Now again, we want our results to end up with 12k, well, just some 12k plus 1. Or in another way, we want to make to end up with the c squared is going to be in the form 12k plus 1 quantity squared. So our scratch word is gonna be look like this. We have or we can use a new word. We obtain, doesn't really matter. Obtain. We have c squared is gonna be equal to 12k plus 1 quantity squared. And again, we need to factor this out to give us 144k squared plus 24k plus 1. Now, of course, we need to figure out what A and B got to be in order to end up with this result. So if we try to analyze it this way, we have clearly when we have the form 12k plus 1, we have c equals 13 as the first number. And in that case, we have 5, 12, 13. And then if we set our k to be 2, oh, okay, this actually works. This actually works. It does. It can be. It can include. My bad. So we set a k to be some positive integer. Okay. So right. So in this case, we actually include. When k is equal to 1, we actually start with 13. Okay. All right. All right. Then when c is equal to 25, we actually get 7, 24, 25. And then if we keep going, let's say if we set c to be 37, we actually can get something like, let me think. I believe it's going to be 12. Let's see. We have 35, 12, 37, but let's see. 25, 24. Let's see. We said 37, right? So yeah, for 37, we end up with something like 35 plus plus 12 35 comma 12 comma 37. So how do we set it up? Well, we're going to trying to end, if we try to list out the aids and the um the per, primitive Pythagorean triples here, we actually end up something like that does not have a good form, in fact. So we will get something like no, we said 13 as a minimum. So we have 5 comma 12 comma 13 as our first one. Then we have let's see, we have 7 comma 24 comma uh, 25. Now, the next one you might think will end up with 13 and 30, 37, but unfortunately, this is not how it works. Because if we're trying to take the difference like that, we actually don't have very nice form. We don't have an a to be an integer. So in fact, we actually get some. We actually need to take this one. This is the only one that we actually have. Um, and then after that, we have 49, and 49 itself is also a perfect square, but it does not really matter in this case. We actually can come up with something that I don't remember what it's gonna be. So for 49, we actually have permit for 49. So uh, see, let me see. So this one is I'll leave it open because this is actually not quite easy to make. 549. If in fact, I don't think 49 is actually going to work. So let's try to take a look all those primitive Pythagorean triples up to 100. If we try to include those, we actually end up with the following list. Um, we have 3 comma 4 comma 5, and then of course we have the 5 parts. Well, we have 13. Then we have 17. Actually, if we try to include 17, we actually get something like 15, 8, 17. Of course, there's no 21, and then 25, there is 29. We have 20, 21, 29. And then we don't have 33, we have 37. And then we have 41. In fact, it's very easy. Uh, 41. And after that, surprisingly, well, of course, there's no 45 as we expect, but there's also no 49 under our, which is supposed to be under our expectation. After that, we have 53, and then we have 61, and then so on and so forth. Not here. For some reason, it just did something like this. Again, here, lower dots like this. So again, this question is a lot trickier, and this is the reason why like at the beginning of the problem, it mentioned that it's actually hard to prove, and sometimes our assumption might not be correct either. So first, I'm going to leave it. I'm going to leave it open like this. Um, And again, I'm going to put a question mark at the beginning because our assumption is once again not so correct. So I'm going to leave it open like this, and then we're gonna come back later. Well, let's not spend too much time on this. Okay. So let's go back to where we end up. Last time we ended up at problem 8a, which again, let's start with the instruction first. Let m and n be numbers that differ by 2 and writes the sum 1 over m plus 1 over n as a fraction in lowest term. For example, 1 over 2 plus 1 over 4 is equal to 3 over 4. And 1 over 3 plus 1 over 5 is equal to 8 over 15. And then for part A, compare the next three examples. And we found that we have 5 over 12, 12 over 35, and then 7 over 24. Now, part B is asking examine the numerators and denominators of the fraction in part A. Of course, we also should include the two what is it called, the two fractions in the example. Okay, so that we have actually more data to analyze. And compare them with the table of Pythagorean triples on page 18. Formulate a conjecture about such fraction. So if we take a look, go back to here, I'm going to switch to the textbook page. So the textbook is this one here. In chapter 2 and page 18, which is actually the end of the chapter before we go through the um, exercise. Okay. Uh, Again, in this textbook, I gotta mention something that we when we say the set of natural numbers, we do not include zero here. Okay, just for this textbook or this course, we do not include zero as part of the natural numbers. If we include zero, we will just call the entire set the whole number set. Okay. Anyway, the table here on page 18 shows that if we try to look at the fractions, um, we have the numerator and denominator will either be A or B. Of course, it will actually take the numerator is going to be the smaller value, where the denominator is the bigger value. Such as when we take 3 over 4, we have the 3 to be the numerator, the smaller value, and then the denominator is the bigger one, which is 4 here. And then when we have let's say 1/3 plus 1/5, which ends up with 8 over 15, we actually end up with 15, which is a bigger value, is appeared in the row 5 comma 3. And then the smaller value, well, is going to be the even number in this case, is the numerator of that row. So based on the table that we have, we actually can try to come up with something. Okay, so uh, we see that first of all, for 1/2 plus 1 over 4, that is going to give us the first row. And if we set 3 and 5, it actually ends up with the fifth row here. And then when we have 4 and 6, we actually end up with this row 5 comma 1. And then when we have 5 and 7, we end up with, which row is it? We have 5 and 7, which is when s is 7 and t is 5. And then when we have 6 and 8, we end up with 7 and 24, which is going to give us 7, 1. Okay. So how is that going to help us? Well, in fact, we can come up with a small conjecture that uh, when we have Um, we can try to list out a few more if we try to go deeper, but basically we can assume that the numerator is going to be the minimum of A and B, and then the denominator is the maximum of A and B, of course. Now, on the other hand, which row does it belong to? We actually need to figure out as well. So, if we're going to come down here, let's try to list out a few more and see what's going to happen. Go back to our page here. We have gain the solution. Let's try to list out a few more. So I'm going to first try to do a comparison. Well, if we have let's see. So we're gonna list all of them out, and then we're gonna list a few more later on and see what's going on. And again, we already have five of them. So we're going to list out five more and see what's going on here. So we said 1/2 plus 1/4, 1/4 is giving us 3/4. 1/3 plus 1/5. Again, cross multiply, and we sum add the denominators, to be our new numerator, and take a product to be our denominator. Of course, if needed, we will actually do the what's it called? We're going to do simplification or cancellation if the denominators are both evens. So such as 1/6 plus 1/8. Cross multiply, we get 14 on top, but we need to divide by 2 because 2 will be the common denominator. Well, greatest common denominator, divisor of the denominators. So it'll end up with a 7 here. And then on the bottom, we have 48/2, which is 24. Next, we have 7 and then 9 here. And clearly on top, it will end up with 16. On the bottom, it's going to be 63. And then if we have 8 and 10, the top is going to be 18/2, which is 9. The bottom will be 8 times 10, which is 80 divided by 2 is 40. So similarly, we have 9 and 11. We end up with 20 and 99. And last but not least, we have two more to help us. We have a 10 and a 12, which gives us 11 and 60. And then 11 plus 13 is going to give us 24. And then the product is going to be 143. Now, of course, we don't see 143 here ever, but then we also have something like the following. So for the first row, it actually matches up with the first row when s is equal to 3 and t equals 1. So I'm going to do the following. So we have 3 comma 1. Let's mark it down like this. Then for 3 and 5, we end up with 18 and 8 and 15, which is from 5 comma 3. Then next we have 4 and 6 giving us 5 and 12, which is from the row 5 comma 1. Okay. Next we have 12 and 35, which is from 7 and 5. 7 comma 5. And then 724 is from 7 and 1. Then 7 and 9 is going to give us 16 and 63, which is from, nope, I need the quad here, which is from 9 comma 7. Oops. Like that. And then 9 comma 40 is from 9 and 1. 9 and 1. Then 20 and 99, it actually does not show here, unfortunately. And then 11 and 60, it does not show. So let's pause here, and then we're gonna take out the remaining 3 because they don't show from our table. And we're gonna use these as our comparison quickly. So if we look at the odd ones, we just simply end up with s is greater than s is equal to t plus 2. And then for the even ones, we somehow see that, well, we're trying to make our conjecture. We somehow see that the t value is always equal to 1, and then the s value is always equal to the average or the mean of the two denominators. Okay, so maybe we can just come up with our conjecture that, and again, 7 limiter, we compare it with the table, so the formulate a conjecture both if both denominators are odd. And again, because they're different by 2, then we see that then we actually can see that if the denominators are both odds, we are going to take the odd rows where the s value is the bigger one and the t value is a smaller one, and then we will say that the numerator is equal to the minimum of the two values a and b. Now again, do you guys remember what a and b are? If we use the two values in the parentheses as s and t, which is actually from the table, by the way. So there's what we actually get. Again, we have the s value and t value, so that it implies us the a, b, and c, the Pythagorean triples, where a and b are equal to st and s squared minus t squared all over 2 respectively. So in fact, we're going to see that no matter what we're doing, we're going to take the value of the form st, and then this way t s s squared minus no, yeah, s and t based on the denominator that we have. So we're going to take the minimum of st and s squared minus t squared all over 2. Again, for s, the larger denominator, and t, the smaller denominator. Now, on the other hand, if both are even, denominators are even, I shouldn't say odds. This is okay. Are even. Well, we actually can put something like this. Notice that. Okay. We say that if both are even, then the t value is always going to be equal to 1. By the way, okay. So let's jump back to our actual work here. We are saying that if both denominators even, then t has to be equal to 1 no matter what. And we also can see that we actually don't really use the terms that are like 7, 7,3, or 9,5, anything like that. All we take will be just s and t are either different by 2, or when t is always equal to 1. Okay, and again, that's depend on the situation that we have. If whether both denominators are odd or both denominators are even. Okay. So again, if both are even, then we will say that we have this for the numerator will still be the minimum of a and b, where again a is going to be st and b is going to be the fraction as square minus t squared all divided by 2. And of course, the denominator well, to be more correct, the numerator of the sum is equal to this, and the denominator of the sum is equal to the maximum, meaning the larger value of the same thing, okay, between a and b, like this. And again, this also holds true for the odd values. And then, of course, the condition of s and t are actually depend. For odd, on for both denominators are odd, the s value will be the larger denominator, and the t value is going to be equal to the smaller denominator. Then for both denominators even, then this is going to be true for s is going to be equal to the average of the two denominators. It's the average value of not count value of the two denominators, and t is always equal to 1. So this is our conclusion here. And after that, we need to prove that part C, we need to prove our conjecture is correct. Meaning that, well, we clearly have these values going to be true. We're now going to get a little bit more, meaning that now we're going to generalize these ideas um, to make it true. Okay. So now, uh, it's not going to be too difficult to actually check because it's just basic algebra, especially for um, the odd case. Okay, we can see that for the odd case we have 1 over t plus 1 over s, and then we want to show that the top is going to end up with s plus t, or and then let's see, and then the denominator is gonna be equal to s times t. So in fact, we can show that uh, by uh, let's see, we have 15.8, and then let me see what is going on here. So if we ignore the case when s equals 3 and t equals 1, which of course is something that we didn't include because we start for the odd case we start at t is going to be equal to 3 or more. It's either t is equal to 3 and when s is equal to 5, and then or later on will be t equals 5 and s equals 7. But if we try to pay attention carefully, um, if we set our s and t to be both odd, then clearly st itself is going to be odd because odd times odd is odd. But then this odd number is going to yield us the denominator, and clearly we have that denominator is going to be greater than the b value, which is even, which is actually the sum that we're expecting. So in fact, how can we simplify our answers? Well, we say that if both denominators are odd, then on the numerator, it's going to be the minimum. In fact, which one is the minimum? It's going to be the fraction part. So we have this fraction is actually the minimum of the sum is equal to this. This is the denominator, and the numerator would then be just the product is equal to just st. St, like so. Okay, and then again, the conditions of s and t are still remain the same. Okay, now if we look at the even case, we have we still have st to be odd because that's again the numerator, which yeah um, which after divide by 2, if we take the average of the two consecutive even numbers, it has to and yeah, it's gonna be an odd number because if every odd number is between every odd number is between two even numbers. Okay, um, two consecutive even numbers. So in this case, if we simplify that, we have the numerator is going to be equal to st itself, st, and the denominator, and of course, is going to be the even number here. Would then be the fraction. Let's see, and the denominator. So, and again, now we can try to prove our conjecture to be correct. So in fact, um, if we try to take one step further, since t is going to be equal to 1 for the denominator case, of course, we're going to do it in part C when we need to prove it. So part C, prove your conjecture is correct. We're going to begin the solution here. Where are we? Okay, we're down here. So here comes the solution. So case 1, suppose both denominators are odd and again, we actually do need another condition for the odd case. We're not just simply picking s and t. Well, of course, we're saying that s is the larger one, and then the t is a smaller value. But there's an extra condition in this case that s is equal to t plus 2. And again, that is because for now our setup is 1 over some integers n plus 1 over n plus 2. Okay, so if we set our s to be a larger value, then we can rewrite we can actually rewrite our s to be in particular or odd, and we have s is equal to t plus 2 here. Then our proof is going to be the following. We have the fraction 1 over s, actually, sorry, 1 over t, because t is a smaller value, plus 1 over s is going to give us if we try to pay attention to this, we get our sum. Well, the denominator is very easy. It's going to be equal to its denominator is just a product, st. And then the numerator here is going to be t plus s, or s plus t. However, the denominator is already set. We already proved that the denominator is of the form s times t. But then in the numerator, we don't have the form s squared minus t squared all over 2, right? How should we prove it? Well, don't forget, and we have an extra condition that s is going to be equal to t plus 2. So we're going to use that and play with our algebraic skills. That now the top is going to be equal to t plus 2 plus t, which ends up with 2t plus 2. And then again, the denominator is still the same, st. How is it going to help? Well, again, now we need to backtrack what s squared is. We know that s squared itself, by definition, s is going to be equal to t plus 2. Okay, so what we're going to do is we're going to add the fancy zero. How does it work? Well, we still have this term here. But now we're going to add a fancy zero, meaning that we're going to add an s squared. And now, of course, we need to subtract it. Or in fact, we actually can add a t square, and it is actually good enough. Let's take a look at what if it's going to work. If we add a t square and then a minus a t square, and of course that's because we actually want a t square somehow. Okay, then this is going to give us, if we combine all these fractions together, well, so far we have something like this. Then what we need is we need to, in fact, on top we want half of it. So in here, instead of adding t square, maybe we should change it to half of t square. Half of t square. Okay, so here we're going to do the same thing. But then now we are going to multiply the 1/2 to multiply that 2 to the denominator, just for the moment, so that it's easier for us to calculate. Now again, that is going to give us, the first term doesn't change. The second term is going to look like having a 2 in the denominator instead. So I'm going to simplify it this way so that we're not going to see too many lines here. But it's just basic algebra. So again, we're now adding what's so-called a fancy zero here, so that we're not going to change the value of the entire thing. But then now we're going to actually multiply two on both top and bottom of the first fraction, so that now we actually can find a common denominator of all these things, which is gonna be 2st. What does that do to our game? Well, now as they have common denominator of 2st, we can just add all these together. Now the first term is, as we multiply it, we have 2 times 2t is 4t, plus 2 times 2, which is 4, and then plus the second term is t squared, minus the third term t squared again. That is going to give us, as we try to combine the first 3 terms together, we actually get a perfect square of t plus 2, quantity squared. Okay, t plus 2, quantity squared. And now, of course, last but not least, we have the minus t squared here. Okay, which gives us, again, by our assumption, our s value for this case is equal to t plus 2, to give us s squared minus t squared divided by 2st. And again, we can just bring the 2 in the denominator to the top as a fraction to end up with the results that we expect. Which shows that the numerator is equal to the fraction as square minus t squared all over 2, and the denominator is equal to the product st as desired. Okay. Now we just finished the case when both denominators are odd. Now we still need to finish the case when both denominators are even. So I'm going to take a 5-minute break and then come back and continue it. Meanwhile, if anyone is watching, you can just try to take a look and try to think of how to come up with the solutions. Okay, if we can now, as we continue for the even case, so we have something like the following. Suppose both denominators are even and t is equal to 1. And then with our setup, I'm not going to special specialize what we actually need to do particularly, but we should know what we're trying to say. So in this case, what our setup is gonna be look like. Well, we're saying that the s value is gonna be the difference. Well, not the difference. It's actually gonna be how should I say it? The s value is going to be the average of the two even numbers. So in fact, more precisely, we see that the difference of the two denominators is going to be separated by 2. Then the odd numbers in between would be the average of the two denominators. So in fact, we actually end up with the first term is going to be 1 over the quantity s minus 1, which is the even number, that's just one smaller than the s value. And then for the second part, we have 1 over s plus 1. And therefore, if we try to add them together, of course, first we're going to end up with s minus 1 plus s plus 1 on top, which simplifies to 2s. And then the denominator is just going to end up with s squared minus 1. And again, that is going to that's actually based on the what's it called, the difference of squares. Now recall that our setup of t is going to be equal to 1. What we can do is, of course, we're going to multiply. We can actually multiply by 1 on top and 1 on bottom, or call the fancy one. Okay, where we are going to write it like the following. Actually, we don't have to multiply the denominator, but what we're going to do is we're going to write as the following. The top, we're going to multiply by 1, which is a fancy one. Now, why is it fancy? Because we're going to rewrite the 1 into t by substitution. And then on the denominator, we are going to rewrite s squared minus 1, in particular the part minus 1, into minus the quantity 1 squared, where again 1 in our case is going to be equal to the t value. So we actually end up with something like this. We just end up with the top to be 2st, where the denominator is s squared minus t squared. And last but not least, we can divide both top and bottom by 2, such that on top we just end up with st, and then the bottom we have the quantity s squared minus t squared, all divided by 2. And again, this is how it will look like in our solution. Which shows that the the numerator is equal to st, and the denominator, the denominator is equal to the fraction as desired. And that completes our proof, and proof our conjecture is true. Last but not least, we have problem 9. Again, we're going to try to end this chapter by today. And if we have after if we can finish problem 9 today, great. And then we'll use the rest of the time to go back to the part that we skipped. If not, we'll continue next time, and then hopefully again finish chapter 2. Uh, Ideally today. If not, definitely try to finish it next week or next time when we do a live stream again. So last we have problem 9. Read about the Babylonian number system and write a short description, including the symbols for the numbers 1 to 10 and the multiples of 10 from 20 to 50. So we are go back to our textbook because if I remember correctly, we actually do have a like a page to that mentions the number system. Uh, but I'm not sure. I need to take a look if it's here or not about the system. Actually, we don't have it here. We actually need to go and find out something like that. So instead of finding from the textbook, which actually does not is not there. Uh, Again, even if we move on to the next chapter, it's not going to show up a lot about the Babylonian system, number system. So let's say we're going to Google it and see what's going on. Babylonian. How do you spell it? Babylonian number system. It is in well. First, we actually know that it is actually a base 60 uh, system. But then, more precisely, we actually can take a look those numerals, which looks like this. Let me see. We actually have something like this. This is the Babylonian numerals. So we actually see that from 1 to 9, they just use instead of using 9 different symbols like what we have nowadays. They're just playing like putting sticks together, but instead of having a stick, they have a like upside down triangle on top with a stake to count to count 1, and then they just use as many copy as they need to count up to 9. Okay, so like uh, we can just use a stick to represent 1, 2 sticks to represent 2, 3 sticks as 3, so on and so forth, like this, like or like counting numbers with fingers. Okay, um, but once they hit 10, they don't use 10 symbols or 10 copies of that symbol to represent. They're going to use like you can think of like an eye or an eye symbol or like um, um, a tweak symbol of 1, um, or you can think of like some people some mathematicians argue that it was a symbol of like a bird maybe or like a the tail of a fish, something like that. But it doesn't really matter. It's a symbol. But the idea is that for 10, they're going to use a different symbol to represent it. And we see that after that, we're just adding them together. And then we have 10, 20 is just 2 copies of 10, 30 is 3 copies of 10, so on and so forth. So in fact, it is actually quite similar to to the old counting system, except now when we are trying to bring the digits to 10, they actually use a new symbol to represent it, and then it goes up to 59. And after that, where's 60 at? We actually don't see a 60. That's because the Babylonian numerical system is actually a base 60 system. So in fact, even though they're using 2 different symbols to represent 2 types of numbers, ones and tens, the way that they actually carry the numbers carry a one for every 60 instead of carry a one every 10 like what we do nowadays, such as when we do addition like let's say 58 plus 65. Of course, as vertical addition, we'll just do it from right to left. Then we're going to do 8 plus 5 first to end up with 13, and then that extra 10 here, or we'll write as a 1 and carry it to the next digits. So similarly for the Babylonian numerical system, they're gonna carry a 1 for every 60, such as if we have 36 plus 47, that is going to give us 83. But then we're going to, 83 is actually bigger than 60. So we're going to carry a 1 to the next digits and then figure out the remainder, which is 83 minus 60 is 23. So we end up 1 as the second digit, and then 23 as the first right digit. Okay. So numerically, we can also write as 1 comma 23. So uh, write a short description, including the symbols for one and for numbers 1 to 10, and multiple from 20 to 50. So we are going from here. How are we going to answer it? Well, again, here comes our solution. Well, it's not really a solution, but like we're trying to answer it. We can. Do I? Let's see if I actually have A and S here. I do have it. Okay, perfect. And I'm going to remove this. No, no. Yes, like that. So what's our answer? Well, our answer is gonna be, well, just a short description. The Babylonian number system is a base 60 numeral system that uses two, well, let me use two different types of symbols for ones and tens. Such as 9, 9 is equal to 1 times 9 is written as 9 copies of one of the symbol of 1. And then let's say 30 here. 30 is equal to 10 times 3. Actually, more precisely, I should switch around. Okay. Remember, there even though the results will be the same, the meaning will be different. The first term is telling us how many copies, and then and then times whatever is actually telling us what is being multiplied. What is the actual object that's being multiplied? Okay, so we have 3 copies of the tens in this case. Okay, is written as 3 copies of the symbol of 10. Now, of course, we can actually do something like that. Um, let's say we have something like 39 this time. Then we will write it as 9, well, 3 copies of 10 plus 9 copies of 1. Okay, is written as 3 copies of the symbol of 10 and 9 copies of the symbol of 1. And again, we can actually verify from the example on charts here. Okay, 39 is developed into 30 plus 9, where 30 is actually 3 copies of 10s, and then the 9 part is just showing 9 copies of 1. Okay, now again, we also need to mention the last part. However, as a base 60 system numbers such as, let's say, for example, 83 is going to be written as 1 copies of 60 plus, and then remainder is 23. Again, 23 is developed into, I'm going to put parentheses here. Okay. Parentheses 23. Again, 23 is going to be written as 2 times 10 plus 3 times 1. Okay. Would contain a space. I would say possibly. Sometimes the space will not be that obvious. We can actually see an example here later on. Okay, we can try Google it up and see what's going on. Possibly contain a space between the $60 digit and the 1 digit. Kind of like a placeholder that we're talking about. Okay. Well, it's kind of like in the placeholder, like a 0. Okay, but then they don't have the symbol of 0, by the way, so it is a little bit different somehow. And then we can have something like let's say for example, let's say 7373. Okay, so I don't know what that is either, so let's take a look what's going to give us. This is going to give us, well, if we're gonna divide by 60 squared is going to be 3600, and then double it will be 72. So this is going to give us 2 times 60 squared, and that is going to end up with 173. And 173 is going to give us a 2 times 60, and that is 120. Subtract that, that's going to give us 53 at the end, plus the quantity. Again, I'm going to put parentheses to know as is going to give us 53, where 53 is going to be written as 5 copies of 10s plus 3 copies of 1. Oh, so that is going to say that we'll end up with 2 symbols of 1. Um, well, I should say 2 symbols, 2 copies of the symbol of 1. A space, and then a space. And again, the space is actually trying to separate between the 2 different digits. Again, that is because they're using symbols instead of using different they're using the same copies of symbols instead of using different symbols to represent uh, different numbers. So they actually need to have some separator in order to identify where the digits end and where the digits starts. And then 2 copies of the symbol of 1 again, and then a space. You can think of like a space bar, or like having a space bar entered once, okay, to do a small separation. Then after that we have 53, and then we have 5 copies of the symbol of 10, and 3 copies of the symbol of 1. Now I'm going to put a note here without spaces in between. Okay, so what does that mean? Well, let's say we're going to Google it again. Okay, we're going to Google. Um, so we have Babylonian uh, number of, let's say, 73, 73. So I'm going to use different examples here that I found on the website, on Google, and then it will actually lead us to a different website. So we get in this example here. Let me see if I can actually open it in a new image here. Let's make it a little bit bigger. Okay. So we actually see that 60 looks exactly the same as 1. And then when we have something bigger than 60, such as 75, we need to break it into 1 copy of 60 times 15 times copies of 1. Okay. And then inside of the 15, we need to rewrite as 1 copies of 10 plus 5 copies of 1, of course. So we actually will see a 1 isolate, and then there's a small gap between the 1 and the next the symbol of 10. And after that we have the symbol of 10 attaching to 5 the 5 copies of 1. Okay, so this is what it means by having a small space between the 2 digits. Okay, where in this case the 10 and the 5 are considered as the same digits, so there's actually no gap in between. Okay, similarly, if we have something like a 1002, we can if we divide by 60, we actually have 16 remainder 42, meaning that our first right digits is going to be 42, and then the second digits is going to be 16 separately. Then for 16 we'll just use the symbol of 16, and then we'll put a space in between the 2 digits, and then for the first right digits we'll just put 42. Okay, so that's what it meant by having a gap. But is this a good way to count numbers? Of course, no. First of all, we actually need to do counting based on how many copies we have. And second of all, we are not using different symbols. We're actually using the same symbols repeatedly for different digits, and even worse, we don't have a placeholder of zero in our in this Babylonian number system, meaning that we cannot do something like 102, like we have in our numerical system. Okay, so what I meant is, let's say if we have 3,600. Again, that is 60 squared. Okay, which is gonna give us the one copy of the one symbol, and then we don't have anything after that. Just like a 60, we just simply have a copy of the one symbol here, but then we will not be able to tell whether we are mentioning a 1, a 60, or a 60 squared, because there is no zero in this numeral system, and we won't be able to identify without any placeholder. Okay, so this is the answer of part A. Now go back to the problem here. We have part B, which says read about the Babylonian tablet called Plimpton 322, and write a brief report including its approximate data of origin. So, what is that tablet going to tell us? Well, if we're trying to look it up online, again, it is not going to. It's not mentioned. Well, it's barely mentioned in the textbook, but then more of the time you actually need to look it up on website in order to see what it actually really does. So let me try to share it again on Google. Uh, this is the what's it called? This is the Plimpton 322 tablet, which is uh, which is a tablet from years ago. Uh, Before, in fact, it was they believe it was before Pythagoras, and we have a paper version here, and let's see if I can show this as a larger image. Okay, here we go. So we have something like this. Uh, if we turn it into digital, this is how the tablet look like. We actually see a couple columns here, and then these symbols, once again, numbers in the Babylonian language. And what does this tablet tell us? Well, if we're um, trying to read some articles such as Wikipedia. I know sometimes people say Wikipedia is not reliable, but then if it is something that is very general or something that is very common. There are a lot of people who actually try to proofread it and make sure that they're not too far off. So for this tablet here, the article is actually quite accurate. So we can see that on Wikipedia, it says that it's a tablet that was believed was written about 1,800 BC. So in fact, it's almost 4,000 years from now. Well, clearly it's a mathematical table because it has all the math. No, it has all the numbers there. Okay, but what is this tablet going to be about? It is actually found out that each row of the table is related to a Pythagorean triple. So in fact, we can try to look at the tablet again. Well, it is actually a lot of numbers there, such as the first row. If we ignore the very big part of on top here, The first row starts off with a 1 plus a 5, a 10 plus a 5 is 15, and then after that we have something like some other values here, and then yeah, and then the last row um the last column of each row is telling us the row number 1, 2, 3, 4, and so on and so forth. Of course, there is something missing from the tablets because it's over many millenniums, so um, is damage is understandable. But anyway, um, we can see that there are numbers there, and based on mathematicians who study, they figure out that each row of the table is related to a Pythagorean triple. And then let's see if there's anything um, anything that's more important. Okay, so we found well in this article it says that um, two mathematicians uh, saw this tablet as a study of solutions to Pythagorean equation in whole numbers. So it's related to number. This suggests a number theoretic motivation. So it's number theory related for Pythagorean triples. So it ends up with the three numbers in the middle. Okay. Again, we actually see five different sets of numbers in each row. We have first one we have 15, and then we don't know what that is yet. But then the last one is telling one of the row number 1, 2, 3, 4, 5, so on is not related to the actual calculation itself. But then there are three sets of numbers in the middle, and we actually see that the conclusion from the mathematicians set is actually the set of three numbers. 1/2 times x minus 1 over x, comma 1, comma 1/2 x plus 1 over x. And again, in this case, we see that the numbers that they're using is not just integers. Again, it mentions that it's a finite sexagesimal representation, and that term here, sexagesimal, is the meaning of base 60, and then of course, as mentioned, they don't have the idea of placeholder, as well as indicators. So they when they mention when Babylonians write down the numbers, they have a hard time to, well, not really hard time. They maybe it's not hard for them, but then it's hard for us to understand what the numbers are. And in fact, because they don't have the concept of placeholder as well as indicators, sometimes if they need to write as fractions, and they'll also write kind of like an integer. So that's why when we see symbols like that, sometimes it might be referring to a finite a finite representation of of a fraction instead of just an integer, such as 1/60. They might still use a symbol of 1, because for them it's just same as moving the digits around by shifting the decimal points. Well, to us it will be decimal points. 1 unit to the left, 1 unit to the right, things like that. Okay. Um, which gives us this result here. Now, again, of course, if we really want to bring it into Pythagorean triples with integer, integer values, all we need to do is multiply all the terms by x here, so that now we'll end up with 1/2 times x minus 1 as our a value, and then 1/2 times the quantity x squared plus 1 as a c value. So and then of course the b value is going to be equal to x itself, such that all three terms are going to end up into integers. So in fact, what they did is they simplified the b term into 1 instead of x, such that instead of having integer solutions, we have rational solutions for each row. So we end up with rational Pythagorean triple. Okay. Okay. So including as approximate date of origin. So back to the textbook question. It says read about the Babylonian tablet, which we did, and write a brief report. Of course, we just simply can write down what it does. But then it also mentioned that includes its approximate date of origin. So we can just look back up on Wikipedia and see it says that it's been written around 1800 BC. Okay, and then we actually don't really know when, like an exact date. But if we go back to the tablet, we can kind of see, we can take a look and see if we can figure out where it says 1800 BC. Okay, so if we think of the term 1800 BC, we actually don't really know because that will the way that they count the date will be different from how we count dates. So it doesn't really it's actually very hard for us to figure out where they actually put down the date and other information besides numbers on this tablet. And besides, we actually don't know their language. We don't know how to analyze it. So anyway, based on the information that we read from the article on Wikipedia, we can answer in the following way. So our answer is, again, with this answer, the Babylonian tablet uh, believed to have been possibly written in 1800 BC is a tablet, of course, by Babylonian. So I'm not going to write that. Well, we believe it's a mathematical. Well, they actually proofread it and yeah, agree that it's a mathematical uh, tablet of the study of the uh, Pythagorean triples. But in this case, it's going to be rational Pythagorean triples of the form, not of the from. And again, we need to write down what the form looks like. We have what? Let me put it like this: left, and then of course we need the right as well, because we have fractions here. We're gonna put it large. So we have what did it say? Again, we have this here. We have x time plus. Oh no, not x plus, x minus 1/x, and then we have to close it. Oops. And then comma. The middle term is always equal to 1 for some reason. And then the c term is going to be uh, fraction 1/2. Um, what is it? Oops. Why is it 1/2? No. We are 1/2. It's going to be x plus, oops, plus fraction 1/x. like this. And of course, this is in base 60, uh, in base 60 numerical system, numeral system. Yeah, we can briefly say something like that. Again, this is and then for the number, for the big number on the left, this possibly will so this okay. So it didn't really mention much of dating. Okay, around this. So based and if we're down here on the Wikipedia, to be more precise, they believe that it is in yeah, in around 1800 BC, and then with plus or minus 22 years. Actually, less than 22 years. Yeah, it's a period of 36 years. But anyway, close enough. Um, and again, yeah, it mentioned that some some um the number on the far left will we actually have something that is not related to the angle, but then it's an approximation of the side limbs that are close to some of the angles, so that they will be able to get uh, the values that are in some kind of order. Okay, so this is it for part B. Now we end up with part C, and then it's already time. So we're gonna continue um, next time on the yeah on next week, next Thursday, to be more precise, and we're going to uh, finish chapter 2, including hopefully problem 3C that we didn't solve this time either. Uh, and then after that, we're going to move on to chapter 3. Okay, I'll see you guys in the week. I'll see you guys next Thursday.